So there's the helicopter. Here's the ground. Time equals 0. You have to choose as the instant the object is dropped. Time final is the instant it hits the ground. And then for the coordinate system, I'm going to put it on the ground beneath the helicopter at the instant it's dropped. And the orientation with the x-axis horizontal in the direction of the motion. Then the initial position is 0, 45. The final y position is 0. We're looking for the final x position because the displacement vector is the final position minus the initial position. The initial velocity is, well, we need to calculate that. That is, what did I say the speed was? 40? Yeah, so this is going to be 40 times cosine of 20, 40 sine of 20. And what do you get for that? Okay. Okay. Does that look right? Okay. The acceleration is 0, negative 9.81. Oh, thanks. And we don't know time final. Is there an equation we can use with these values? No, because we don't know the, well, so that's sort of an interesting one. If you think of it this way, that the x component of the final velocity is going to, like the x component of the velocity never changes because there's no acceleration in the x direction, then you might look at this and say, well, we know that the final, like, VFX is still going to be 37.59. So it looks like this all works. But you end up with 2 PFX minus 0, or 2, yeah. You end up with 2 times 0 times this is equal to 37.59 squared minus 37.59 squared, and you get 0 equals 0. So it looks like it when you look at the variables that that'll work, but it ends up everything cancels out and it doesn't help you at all. So I think the answer is there's not an equation that works. So we're going to have to find time final. So PFY 0 is equal to 45 plus 13.68 times TF minus 4.905 TF squared. Can we do this with a square root, or do we have to use quadratic formula for that? Yeah, quadratic formula. So I don't have a calculator down here. Can someone tell me what they got or calculate that? Do you know what the negative one was? Okay. Okay, yeah. I'll average. And you get some negative value too. I don't know what that is, and I don't care. Okay, so 4.73 seconds. And now we can go to the x equation. P of x is equal to 0 plus 37.59 times 4.73 plus 1/2 times 0. And so you get an answer that's just 37.59 times 4.73. What do you get for that? What? Okay, 177.8 meters. And then that wasn't exactly what was asked for. We're trying to calculate the displacement vector. The displacement is PF vector minus the position initial vector. So that is 177.80 minus 0.45. And so you get an answer of 177.8 negative 45. Any questions about that? All right, the last thing I want to talk about in 2D kinematics is interpretation of acceleration in 2D, because there's something new that happens in 2D that didn't happen with one-dimensional problems. So 2D accelerations. Remember that in 1D, a non-zero acceleration meant one of two things. Either the object is speeding up or the object is slowing down. So speeding up and that happened if the velocity and acceleration were in the same direction, or slowing down, and that happened if the velocity and acceleration were in opposite directions. But in 2D, there are more possibilities than that. You can have non-zero acceleration where the speed stays the same. And the difference is, in order to have a non-zero acceleration, what you need is to have the velocity change, okay? Right? So think of the definition of acceleration. Acceleration is equal to the velocity at some instant t2 minus the velocity at some instant t1 divided by t2 minus t1. In order for that to be anything besides zero, what it takes is this velocity and this velocity just have to be different. They don't have to be different magnitudes, they just have to be different vectors. And so what we have in 2D that we didn't have in 1D is you can have accelerations where the speed stays the same, but the direction changes, okay? So a non-zero acceleration happens if the speed is changing or if the direction changes. Yep. That's right. So, yeah, exactly. In 1D, you know, the direction can change to the opposite direction. In 2D, though, you know, there's all infinitely many choices of what direction you can go from and to. And so that's the fundamental difference between these. And so I just wanted to go through a few examples with simple numbers to try to sort of help you wrap your head around how acceleration relates to speed changes, but also direction changes. So let's say that at our instant t1, and let's say t1 is equal to 0, the velocity vector is equal to 0, 1 meter per second. Okay. So first of all, what does that velocity vector look like? It's straight up in the positive y direction. So this is the, you know, so that's 0, 1. And let's say that at instant t2, and let's say that that's 1 second. No, sorry, erase that. Let's say that we have an acceleration of 0, 1 meters per second squared. What's the velocity vector at t2 equal to 1 second? Okay, so you can actually use this definition of acceleration to figure out what that vector would look like. Before we go through the calculation, just intuitively, what do you think is going to happen here? So we have a velocity vector at the first instant that's going in the positive y direction. Now we have an acceleration that's also in the positive y direction. What do you expect the velocity vector to be at a later time? Faster, slower, direction change? Faster. So in that sense, the relationship between acceleration and velocity are just like they were in 1D. If you have an acceleration that's in the exact same direction as the velocity, it's going to speed up. And we'll see that if you have an acceleration in the opposite direction exactly, it's going to slow down. So here's how this calculation works. The acceleration is 0, 1. The velocity at time t2 is what we're trying to calculate. T1 minus T2 is 1, so that just cancels out of everything. The initial velocity is 0, 1. And so add 0, 1 to both sides, and you get that the velocity at time T2 is equal to 0, 2 meters per second. Sped up. exclamation point. Okay, so that makes sense, right? I mean, based on our understanding of 1D stuff, that's consistent with what we would expect from 1D. So now let's go to the second one. So say that we have question. Yeah. So for the second one, we're going to start with that velocity vector of 0, 1, and say that we have an acceleration of 0, -1. Okay, that's in the opposite direction. So the acceleration is 0, -1. That's the opposite direction of the velocity at time 1. So based on what we know about 1D kinematics, we'd expect it to slow down. So go back to that definition of acceleration, and you have 0, -1 is equal to the velocity at time 2 minus the velocity at time 1. Add 0, 1 to both sides, and you get that the velocity vector at time t2 is equal to 0, 0. Okay, so it slowed down. Now here are the two examples, the two cases that don't have an analog in one dimension. So first, let's say that the acceleration vector is 1, 0. Then go to the definition of acceleration. We have that 1, 0 is equal to v2 minus 0, 1. Add 0, 1 to both sides, and you get that v at time t2 is equal to 1, 1. Okay, so let's think about what this looks like. Our velocity at time t1 was like this. What does this vector look like? 1, 1. What direction is that pointing? Yep, that's pointing this way. Oh. Okay, so in that example, where the acceleration and the velocity are in different directions, they're not in the same direction or the opposite direction, the object turns. And it always turns towards the acceleration. Like it doesn't become the same direction as the acceleration, but you can see that this object, we had an acceleration that was completely to the right, and this object turned toward the right. Okay? Let's just do an acceleration going the other way to the left to see that this holds. I'm sort of curious myself. So the acceleration vector this time is -1, 0. the definition of acceleration says -1, 0 is equal to the velocity at time t2 minus the velocity at time t1. Add 0, 1 to both sides, and you get that the velocity at time t2 is equal to -1, 1. So this is the velocity at time t1. The velocity at time t2 looks like this. So again, we have an acceleration vector, this time going to the left, and it's making the object turn to the left. Okay? So, notice. First, if the velocity and acceleration are in the same direction, then the object speeds up. If the velocity and acceleration vector are in opposite directions, the object slows down. If the velocity vector and acceleration vector are not parallel, okay, so these first two cases, the velocity and acceleration vectors are parallel in one way or another. Then the object turns toward the acceleration vector. Okay, so if an object is rolling this way, I guess let's do it in 3 different cases. So let's say this is instant A, B, and C. What's the direction? Point in the direction of the velocity vector at A. So the velocity vector, the direction it's traveling, is going to be parallel to that surface. So that's the velocity vector. This thing is turning sort of to its left, you know what I mean? It's turning, you know what I mean? Turning left, right? So what direction, point in the direction that you would expect the acceleration vector to be. So the acceleration vector needs to be some version, something roughly in that direction, right? Okay, so that's intuitively what's going on. If the object is also speeding up, like it would be if this is under the influence of gravity, right? It'd be slower up here, speed up as it gets towards the bottom. the acceleration would have some component pointing that way, and also some component pointing in the direction of motion to make it speed up. And so the combination of those would mean the acceleration would look something like that.
Why is the acceleration
This way? Why is it not? Yeah. Okay, so the acceleration here has, you can think of it as having two parts. It has a part that's making this thing speed up, and it's having a part that's making it turn to the left. Okay? And the net effect of that, if you add, let me draw them like the way vectors add. The net effect of that is an acceleration vector pointing like this. Okay? What's the velocity vector here? What direction is it pointing? At that instant, it's moving horizontally. So the velocity vector is like this. Okay? At that instant, when it's at the lowest point, it's not speeding up or slowing down. All it's doing is changing direction because of this circular path. Since it's not speeding up or slowing down, there wouldn't be any part of the acceleration that's parallel to the velocity. The only acceleration would be making it change directions. So that would be the acceleration here. And now up here, the velocity vector is parallel to the surface that way, because that's the direction it's moving. Under the influence of gravity, would that ball be speeding up or slowing down? Slowing down. And so the part of the acceleration that's parallel to the velocity, would it be in the same direction or the opposite direction of the velocity? Opposite. So there'd be a component like this. It's still turning to the left, so there'd be a component like this. And the net effect is an acceleration vector that way. So that's sort of intuitively how acceleration works in 2D. Let me know if you have any questions about that. I mean, I know it's in that amount of time you can't like fully like wrap your head around that, but I think it's worth it to think about acceleration in those terms when you calculate values in two-dimensional problems. And I think there are actually a couple of practice problems where you're asked to think about acceleration that way. Yep.
would you say that was parallel and perpendicular? Or?
Yes. So yeah, you can break it up into a part that's parallel to the velocity and a part that's perpendicular to the velocity. We're not going to do that mathematically, but you can think of it that way. Any acceleration has a part that's parallel to the velocity that determines whether it's speeding up or slowing down, and a part that's perpendicular to the velocity that determines whether it's turning to the left or the right. Okay, that's all.